radiation comes when you have an unstable atom or an unstable nucleus, and let's say we have something that's unstable. What it wants to do is become stable. And in order to become stable, what these do is they give off radiation. So that's how something like, for example, uranium, that's something that's very common. That's what we use in nuclear power plants. It's unstable, the uranium that we use in those. This is called uranium-235. To become stable, it gives off radiation, and those are the 3 different radiations that we have here. This is higher, guys, so it's not foundation, but a lot of it will be relevant to foundation as well. So yeah, alpha, beta, gamma. I hope you guys know the 3 symbols. That's the most important. That's the basics that you need to know. Alpha is like a fish. Beta is like a bee with a tail on it, and gamma is like a fish that's falling down. So, do you guys know the mass numbers and atomic numbers of each? So alpha, what would the number on top be, and the one on the bottom be? What do you guys think? 4, 2 for alpha, thank you very much. So we put a 4 and a 2 here for beta. And for gamma, let's try and do the same. So beta is 0 minus 1, perfect. And gamma is... Anyone said gamma yet? Gamma is nothing yet. We just put it as a 0 and a 0. It doesn't have a mass, it doesn't have a charge. So we write it as 0, 0. So alpha is made up of, so I think someone already wrote it down somewhere. Yeah, alpha is the first one. Let me write the names down. So alpha is this. Beta. And gamma. So as usual, guys, I'll give you guys a chance to screenshot all of this at the end once we finish the live. So alpha is made up of what? A new helium particle. So it's don't say particles, don't say helium particle, say helium nucleus, because it's not a full helium atom. It's just the middle part of the helium, the nucleus. So helium nucleus, what's that made out of? What's a helium nucleus made out of? Two protons and 2 neutrons. Perfect. So you can either say helium nucleus or you can say 2 protons and 2 neutrons. Same thing, because a helium nucleus is 2 protons and 2 neutrons. Now, what's beta made out of? Someone wrote an electron nucleus. No, you don't. You can't have a nucleus in an electron, because an electron is what orbits the nucleus. It's literally just an electron. A beta particle, a beta minus particle, is literally a fast-moving electron. But in your exams, you can get away with just saying an electron. Good. What about gamma rays? Thanks, Lauren. Yes, it's just an electromagnetic wave. Just electromagnetic wave. That's why it has no mass. A wave can't have a mass, and a wave can't have a charge. So it's 0, 0, basically. It's part of the electromagnetic spectrum as well. It's on one end is the highest frequency end, if you guys remember from waves. So that's gamma. So ionizing power. First of all, what does ionizing power mean? Anyone know what ionizing power means? So think of chemistry. Think of what an ion is. What would ionizing power mean? Ability to knock off electrons, exactly. So in chemistry, when you form an ion, you either remove or add electrons. These types of radiation, when they hit an atom, they do that as well. They have the ability to knock off electrons. The higher the ionizing power, the better they are at knocking off electrons. Then we have penetrating power, which is basically how easily it passes through materials. So the ability to pass through materials. So out of the three, alpha, beta, gamma, which one would have the highest ionizing power? Yep, I do have a YouTube, guys, that I'll post this on. It's a flash revision lab. I'll show you guys that in a second. So highest ionizing power is actually alpha. Alpha has the highest. Lowest is gamma. Good. Beta is medium for both ionizing power and penetrating power. For penetrating power, the highest would be gamma. Thank you. Gamma passes through things very easily, whereas alpha doesn't pass through things. In fact, it doesn't even pass through. What are some of the things that it can get stopped by? What can alpha get stopped by? Paper, good. Paper. What else? What else can... Few centimeters of air. Thanks, Rebecca. Few centimeters of air. That's how weak it is. And one more thing. Yep. Skin. Thank you. Even skin. It can't pass through your body. It can't get into your body. So that's key when we're going to talk about irradiation in a bit. Yes, beta is ejected when a neutron turns into a proton. Yes. So that happens when a neutron turns into a proton. That's why there's a change in, there's a -1 in the number, in the proton number. Beta are absorbed by aluminium. Thank you. That's the key. That's the key material that stops it. You need to know about beta minus decay for AQA. You need to know about beta minus decay. There's beta plus decay as well. That's just for people who learn EdXL. That's something called a fast-moving positron. But yeah, not for AQA. So yes, gamma is stopped by lead and concrete. Thank you very much. All right, so we filled in the table. Let's try some questions and see how we get on. So the questions are going to be relevant to AQA, EdXL, and OCR, guys. So it's just the only thing extra I said was beta plus. You get beta plus as well in EdXL. Okay, so let's go through some questions. First one, how many protons, how many neutrons are there in an alpha particle? We literally just wrote it down now. So what's the first answer going to be? 2 protons, 2 neutrons. Yep, it's not 4 and 2. 4 and 2 are the mass number and the atomic number of protons and neutrons. So protons is always the bottom number. Number of neutrons is always the top number minus the bottom number. So 4 minus 2 is equal to, that's going to be neutrons. Protons is always the bottom number. So that's the answer for that. Excellent. Right, on to the next one. So here we have nuclear equations. So we have the decay of radon 222. Complete the equation by writing the correct number in each of these 2 boxes. So we've got the radon here. We got an alpha particle. So you need to fill in the gaps here. So yeah, I'll keep scrolling back up, guys, and at the end I'll give you guys a chance to screenshot everything. Don't worry. Oh, okay. I see what you mean. Okay, like this. Yep. Got you. Right. So alpha. I think we got some correct answers already. Yes. So basically what needs to happen, guys, the top numbers need to add up. So if you think of just the top part as an equation, we have 222 as our answer is equal to x, that's our number here, plus 4, because we know alpha is 4 too. So you basically need to find what x is. So it's going to be 222 minus 4, which is 218. That's what the top number is, 218. So good, some of you guys got that answer. And then for the bottom number, do the same thing. We've got 86 at the bottom here is equal to, that's an x, that's what we're trying to find out, plus 2. Rearrange that. We got 86 minus 2. So x is equal to 84. So the bottom number is 84. Thank you, guys. Loads of you getting it right. Perfect. So yes, loads of questions like this. You'll get, these are nuclear equations. You can get it for alpha, you can get it for beta, you can get it for gamma as well, but you probably won't get it for gamma because remember gamma is 0, 0. So it won't actually change anything in the equation. So most likely in your exams, you'll get beta decay or alpha decay. Beta is 0 minus 1. Yes, it is, as we got down here, 0 and minus 1. So you need to memorize all these numbers. You got to memorize everything in this table. You get given equations, but there's no equations in this topic. Radioactivity has no equations, so the equation sheet is going to be completely useless to you for this topic. Any questions on this topic? So you need to pretty much memorize everything here. So moving on to the next one. All right, so this is a question on half-life. This is important. Can anyone tell me what the definition of half-life is? What does half-life mean? Average time taken for radioactive isotope to half close. Half the number of radioactive particles to disappear. Yes. Can't wait to half. Yep, good. I'm seeing correct answers here. Number of days for radioactive atom to decay. No, I wouldn't say that. So the way to word it is, so there's 2 ways to word it. The time taken for the number of undecayed nuclei to half. Because remember what's happening. You're starting off with unstable nuclei. and it's becoming stable, right? This is just for one nucleus, so one atom. But when you're dealing with something radioactive, you usually have like a big block of it or something. So you're dealing with millions of these nuclear atoms. So imagine you have 1,000 nuclei which are unstable. So what's going to happen is one by one, they're going to do this. They're going to give off radiation. They're going to become stable. Give off radiation, become stable. They're going to do that over and over again. One by one, they're going to become stable. Each atom's going to become stable. The time taken for, let's say we started off with 1,000. So if we started off with 1,000 undecayed nuclei, so this is something radioactive, and then 500 of them decay, meaning 500 of them now become stable. That means the number of undecayed nuclei have half. So the time taken for it to get from 1,000 to 500 is what we call one half-life. So is this definition wrong? The average time taken for a radioactive isotope to half. I would say the mass. You can say the mass of a radioactive isotope to half, or you can say the number of undecayed nuclei, or you can say the count rate to half. But don't just say the time taken for a radioactive isotope to half, because it's the question is, what about it is halving? So after the next half-life, how many undecayed nuclei will we be left with? So after a second half-life, so this is the first half-life. After the second half-life, you'll be left with 250, exactly. So what will happen is it'll keep on halving, and what that's going to do is it's also going to mean the count rate is halving. Count rate is just the activity. So another definition, so that's one definition. You can also word it like this. The time taken for the activity of a radioactive isotope to half. Either one's fine as well. Is half-life foundation 2? I'm not entirely sure. I'm sorry, you're going to have to check that. I'm not sure if it's foundation. It's definitely higher, and it's all the exam boards need to know it, but I'm not sure if it's foundation. These lives are just GCSE. I do teach A-level physics, but not in these lives. I'll just be covering GCSE. Sorry. So yeah, thank you. Someone answered that. So half-life is in foundation. So yeah, guys, if you know the answers to other people's questions, please reply to them, especially if I don't know the answer. Yep, I will do more questions on half-life. Definitely, we've got loads coming up. So that's what half-life means. Another thing I need to show you is questions where you get given a graph. So half-life questions when you get given a graph. Okay, so you're going to see this. I'm not sure if it will come up. You might get a graph of activity against time. So if you get a graph that looks like this sort of shape, and it's a radioactivity question, most likely they're going to ask you to work out the half-life using this graph. So what you do is you look at the initial activity. So that's the point where it crosses the vertical axis, the y-axis. That's the initial value. To work out the half-life, what do you need to do? Does anyone know what you'll do if you get a graph like this and get asked to work out the half-life? I know people hate graphs, but it's actually, if you think about it, I'll show you, it's actually quite straightforward. You find half of that number. So this initial number, you always read what this initial number is at the top and then half it. So go to half of that, and then you basically get a ruler. Make sure you use a ruler in your exam. Go across to the curve and then go down. So go across, go down, and basically whatever this reading is, that's your half-life. So that reading is your half-life. Cumulative, it's not quite like cumulative frequency, but maybe it's reading off a cumulative frequency line. But yeah, so this is what we're going to do to some of the questions. So let's go and look at some of these questions. So here we got a graph just like that, same shape that I showed you. Use the graph to find the half-life of radon 222. So same thing that I said, always look at where it crosses the y-axis. So it's crossing at 800, find half of that. So half of 800 is 400. Okay, so you go to 400 on your graph, you get a ruler. I don't have a ruler, but I'll try and draw it as straight as I can. Go up to the line and then get a ruler and draw downwards. There, this number is your half-life. So what do you guys think that is? Reading off the graph. Yeah, thanks, Emily. 3.8. And it's as simple as that. So remember, half the value, the top value, half it, go across, go down, and you get the answer. Good. All right, moving on. Next question. A student models the random nature of radioactive decay using 100 dice. He rolls the dice and removes any that land with the number 6 facing upwards. He rolls the remaining dice again. The student repeats this process a number of times. So it's a weird question because it doesn't seem like it's a radioactivity question because it's to do with dice. It's basically trying to show how radioactive decay works. So imagine the 100 dice that you're rolling are unstable nuclei. So you're rolling you've got 100 unstable nuclei, and every time you roll, it's like a certain amount of times passing. So it might be 10 minutes, it might be 10 days, we don't know. And every time, the number of undecayed nuclei decrease. So it basically follows that graph that I just showed you. So it starts off at 100 and it goes down, like so. So that's what this question is trying to explain. And it says, give 2 reasons why this is a good model for the random nature of radioactive decay. So radioactive decay, there's 2 words we can use to describe it. One is random. Oops. Let me move that back. Right, I have messed this up. Let me rub this out. Okay, so 2 words we can use to describe radioactivity. Let me write it down here. Random is one of them. Anyone know what the other word is? Random and begins with S. Spontaneous, thank you. Excellent. So we got random and spontaneous are 2 words we can use to describe radioactive decay. Random, why? Because remember what I said, you have loads of unstable nuclei. You can't predict which one will decay next. That's why it's random. So you can't predict which will decay next. Spontaneous, because you can't control it. So you can't basically make it go faster. You can't make radioactivity go faster. You can't slow it down. So can't speed up or slow it down. Okay, people are not understanding. All right, let me explain. This is just a definition of radioactive decay. So it's just two words to describe radioactive decay. So radioactive decay is when something goes from being unstable to stable. So a nucleus starts off as unstable and becomes stable. Now imagine you have 1,000 nuclei. It's random because out of the 1,000, you can't pick which of the 1,000 is going to decay next, which one's going to do this next. That's why it's random. It's spontaneous because you can't make a nucleus decay. You can't stop it from decaying. It's always going to happen on its own. I hope that makes a bit more sense. Yeah, does that make a bit more sense, guys? Let me know. Yeah, I'll put the whole page in a second. Yeah. Right. So 2 reasons why this is a good model for the random nature. So what is it about rolling dice that makes it good? What do you guys think? For 2 marks, 1 mark for each point. It's random. So you can't just say it's random because it's already told you it's random nature of radioactive decay. So you can't use that in your answer. So what is it about a dice? You can't predict. Exactly. You can't predict. It's unpredictable. So 2 things we can't predict. We can't predict which dice will roll a 6, and you can't predict when a dice will roll a 6. That's why it's a good way of modeling radioactivity. So can't predict which dice will roll a 6, and you can't predict when a dice will roll a 6. Okay, so we're going to now look at a graph. So another graph question. This is about the rolling dice method. Remember I said that it's going to make a graph like this. You can basically treat this like radioactive decay. So we want to work out the half-life. So where are we going to draw a line from? $50. Why does it have to roll a 6? It's just this question, guys. Sorry, 1 second before I go back to this. It's just an experiment they're doing. They want something that's going to be random about the dice. So they said they're going to pick a number 6. So rolling a 6 is random. So they just said, if it rolls a 6, we can model that as a nucleus decaying. They could have picked a 1, they could have picked a 2, it doesn't matter. They just decided in this question to pick a 6. Okay, back to this. So we go to 50. Same method, go across. And then go down. What does that read? 3.6. Yeah, exactly. So those half-life questions, very straightforward. If you see one of those graphs, just remember this is what you have to do. Okay, next question. A teacher uses protactinium generator to produce a sample of radioactive material that has a half-life of 70 seconds. Okay, in the first stage, we've got uranium decaying into thorium, so that's here. determine the atomic number. So what's the missing number here? Remember, alpha is 4 and 2. Yep, we got people with the answer already. It's going to be 90, not 94, because remember, if you look at the bottom numbers, it's going to be 92 is equal to a certain number, x plus 2. We want to find out what x is. So you do 92 minus 2, which is 90. So atomic number is going to be 90. Good, looks like most people got that. Next question. When this decays, new element is formed, and we've got an equation. New element is formed. Use the information from figure 12 and figure 13 to determine the name of the element X. People could find that tricky. Any ideas, guys? What element is this? So what's happened? So let me explain. This has decayed. It was unstable. It's decayed into this new element. What is that element? Answer's not beta. Beta is the radiation. So the question is not asking what the radiation is. It's asking what is X? What element is it? Yeah, I think Jack's got it. Uranium. It's uranium. It's a tricky one. So first of all, how do you know the element has changed? How do we know this isn't the same element? Why is it not just Pa again? I'm going to explain how, don't worry. So different proton number. Okay, so this is one thing we're going to write up there. The proton number, if a proton number is different, so if the bottom number ever changes, it means the element changes. The proton number of a nucleus tells you what element it is. Let's write this down on our notes. The proton number of an element, not of an element, of a nucleus. Tells you what element it is. So if the proton number ever changes, the element is going to change. Okay, so that's one thing to remember. So now the question is, how do we know it's uranium? We know it's uranium because they've pretty much told us in the question up here. So what you need to spot is here, this has a atomic number or proton number of 92. The only other thing that has 92 is here. And they tell us there is uranium. So that means whenever you have anything with a proton number of 92, it's always going to be uranium. But you'll see that on the periodic table, uranium should have a proton number of 92. But in physics, you don't get given a periodic table, so you can't do that. You can't check your periodic table for that. That's only for chemistry. So it's actually in the question over there. So the answer is uranium. Well done for those who spotted that. But that is a tricky question. Right, next one is what everyone else answered for that question. Determine the type of radiation emitted. So it's basically asking, what is this? And I think quite a few of you told me that this must be beta. Good. We know it's beta because it's 0 and minus 1. So that means if we look at the top numbers, 234 is equal to 234 plus 0. Yep, that adds up. And at the bottom, we've got 91 is equal to 92 plus minus 1. Remember, the bottom number in beta is minus 1. 92 plus minus 1 is equal to 91. Therefore, it has to be beta. So 2 marks. 1 to say beta. How would you get the second mark then? Thank you for the rose. Second mark. No one? It's what I forgot who it was. Someone told me earlier. It's because what's happened is the proton number has gone up. So it only ever goes up with beta decay. Proton number only goes up with beta decay because it's a -1 at the bottom. Right, next one. The teacher wears polythene gloves as a safety precaution when handling radioactive materials. The polythene gloves does not stop the teacher's hand from being irradiated. Why does the teacher wear polythene gloves? Anyone know? So it doesn't stop the teacher's hand from being irradiated. What does the polythene gloves do? Beta can pass through polythene and beta can pass through skin. So that's what this question is saying. It says it actually doesn't stop the beta radiation from getting to the teacher's hand. Good. Amaya, to not have direct contact to the source. There's a name for that. Exactly, yep. Contamination. This is all about contamination. So there's two key words here. Irradiation and contamination. Two different things. Two different ways that you can get affected by radioactivity. So the difference is contamination is when particles get onto whatever it is, so onto yourself. Let's say you're trying to stop getting irradiated or contaminated. Contamination is when the radioactive atoms actually get onto you. So if you touch something radioactive, then atoms are going to get onto your skin. That means you've been contaminated with that radioactive substance. Irradiation is something else. Irradiation is when there's something radioactive and it's not touching you, so it might be across the room from you, but the radiation can still reach you. So what this question is saying is the polythene gloves, so the teacher's wearing polythene gloves, it's not stopping them from being irradiated. So if they were not to touch the whatever this is, the radioactive material is, they're still going to get hit with beta radiation because beta travels through the air. Why they wear it is to prevent contamination, because when they touch the radioactive material, they don't want the atoms to get onto their skin. So that's why. I hope that makes sense. So for 2 marks, 1 mark to say it prevents contamination. Because what would contamination do? Why is it bad to get contaminated with something radioactive? Harm cells. Yes. There's a better word than harm cells. Does something to cells. It begins with M. You can say ionize as well. You can say mutates. That's what I was looking for. Prevents contamination, which prevents harm from cell mutation. Or you can say damage from cell mutation. Something like this. Yeah, good. So that's our 2 marks there. All right, next question, 8A. There are many isotopes of this element. What do the nuclei of different isotopes have in common? It's basically, this question is basically asking us to define isotopes, or half of the definition of an isotope. What could you guys say an isotope is? What would you say? What's the definition? This comes up in physics and chemistry. Same number of protons. Good. Same number of protons, different number of neutrons, but this is only asking what do they have in common. It's just the proton number. So same number of protons. Excellent. Next question. It's produced by nuclear fission. So nuclear fission, this is a triple question only. What happens to a nucleus of an atom during the process of nuclear fission? Anyone know? That's just triple, yeah. So if you're combined, then you don't need to know just this particular part. They split. I'm not sure about a deck cell, actually. It might be combined for a deck cell. But yeah, nuclear fission, you can just say they split. So just that section was triple, I'd say. Good. Next. What type of radiation is emitted here? So look at the numbers again. Remember, if it changes, it's definitely not gamma. Gamma is 0, 0. So you need to see how it's changed. We're getting the right answers. Yes, beta, because beta 0 minus 1. 43 plus minus 1 gives you 42. 99 plus 0 equals 99. So it's beta. And you can say the same thing as before. Proton number increases by 1. Good. What is meant by the following statement? Has a half-life of 6 hours. Can we also say atomic mass stays the same? No, you can't say atomic mass stays the same because gamma would also do that as well. Because gamma is 0, 0. So you can't say that. You would have to talk about the bottom numbers, the proton numbers. The time taken for the decay is 6 hours. That's not enough to get you the marks. It takes 6 hours for the number of undecayed nuclei to fall to half. Perfect. So that is looking at our definition. Time taken for the number of undecayed nuclei to half. That's half-life. So if we know our half-life is 6 hours, it means it takes 6 hours for the number of undecayed nuclei to half. That's how we'd word that. Number of undecayed nuclei to half. So you can't just give the definition of half-life in this question. You have to actually apply it to what they've said here. They've mentioned 6 hours, so you have to actually use 6 hours in your answer. Okay, here we have another graph question. All right, this is slightly different. That's why I chose this question, because it works a bit differently. So let's read this properly. So we've got this isotope. It's a medical tracer. It's produced inside a generator. Okay, all of this is waffle. That doesn't help you. In the question, figure 10 shows how the number of nuclei in a sample changes with time. Okay, so we've got the graph that I talked about before. It will continue to produce sufficient technetium 99 until 80% of the original has decayed. Don't worry about these big words, guys. They're just elements. Don't get they're to throw people off. After how many days will a source need replacing? Okay, so a lot of writing here. It's going to throw people off. Let's break it down to the very basics. Okay, we've got a graph. What is it asking for? It's asking for how many days will it take to need replacing, and then we've got here, it will produce sufficient until 80% has decayed. Okay, so it's saying 80%, when 80% of the original decays, that's when it stops being sufficient. So it stops working. Okay, they've just worded it really awkwardly. It's really hard to understand. So what do we need to do here? Draw a line at 20k, exactly. So what most people would do, because of what I said earlier, most people would go to 50k, 50,000, go across and go down. That's not right, because the question is not asking for half-life. It's asking for how long will it take for it to go to 80, for it to have lost 80%. It's not even asking you to find 80%, it's asking when it's lost 80%. If something has lost 80%, how many percent are you left with? %20. Okay, so until 80%, again, they're trying to throw you off. Until 80% of the original has decayed. So it's not saying how much undecayed nuclei is left. It's saying 80% has decayed. So you're actually left with 20% of undecayed nuclei. So that's why you have to draw a line at 20%. So 20% of 100,000 is here. And you do the same method. You draw your line across. And then you draw your line down. What does that read? There we go. 6.2. Yep, well done, guys. Show clearly your calculations. You get a mark for this, guys. So physically do this on your exam papers. Get a ruler. Remember to use a ruler. Don't draw like I did. Get a ruler and draw a line here and here. That's your working out for this. Done. You'll probably get a mark for this as well. So let me write that down here as well. So 800 minus 80 is equal to 20%. So you get calculation marks. So for this and this, you'll get 1 mark. And your final answer is to read it off, which is 6.2 days. All right. Medical traces are injected into a patient's body. This involves some risk to the patient's health. Explain the risk to the patient of using radioactive substance as a medical tracer. So you're basically injecting something radioactive into a person. What's the risk? Is it asking for 2 marks? Damage healthy cells. Yes. Let's write this down in our notes. So risks of radiation. If we have space, it was quite full, wasn't it, our notes? If I can find space somewhere here. Let's get another color. So purple, yeah. So risks of radiation. Sorry guys, this is going to be messy. What I'll do is I'll put a box around it. So risks of radiation is that it causes cell mutation. Because it ionizes and this can lead to cancer. Or it could even just kill your cells. If it's a high dose, it can just kill your cells as well. So explain the risk for 2 marks. 1 mark is to say, what do you guys think? So I think some of you got one of the mark that can harm healthy cell. Harms healthy cells. Can cause cell mutations. Yep, that's fine. Because what would the first mark be? So this is the second mark. It's why does it harm healthy cells? What is it about radiation? What do you guys think? Ionizers, good. Causes ionization. So it ionizes the cell, which leads to harming healthy cells. Good, guys. So those were the questions. So what I'll do, like I said, guys, I'll on YouTube, I'll put these questions up, and I'll allow you to print all of these questions out so you can try them yourselves. So you can print them and try them out with the video. So it's this is the page, Flash Revision Lab, and the ones which say live, you just click on them, and in the comments, you'll basically find the worksheet download. So you'll be able to download it and you'll be able to do it as you go. So yeah. I've also uploaded new types of videos as well. So we've got some videos that say print and practice. I'm going to try and upload more of these as time goes on. So these are like more exam questions or more topics. So this one here is on how to write any chemical formula. And again, it's print and practice. So you go onto the comments, download the worksheet, and then you can work through it as you watch the video. So here, it's how to work out the chemical formulas for all of these. I'm just working through all of these, so you can do it as you go. So yeah, so subscribe to that, guys, if you want more videos or if you want to watch the live again. But let me give you guys a chance to screenshot this and ask me any questions in general. So here is the full page of the notes. So let me know, guys, anything you want to ask me.